All right, good morning, everyone. So welcome back. Today we're going to resume from what left off yesterday. So yesterday we saw our introductory talk from John, and then we had our three speakers giving us some background into their different pipelines. And then tomorrow we're going to continue from that, where we're going to have the same three speakers, so Rainer first, and then Renzo, and then Anna. They're going to guide you through the actual analysis pipeline, and you can follow and also see how different, what are the different options of different softwares analyzing the same data set. So I'll leave the floor to Rainer.
Thanks so much.
Thank you so much for being here again. And yes, looking forward to this. Thanks.
Yeah. This is a nice opportunity to show you a bit how we analyze laminar data in Brain Voyager. And I have prepared a bit points we could do all during this kind of hands-on, but of course we can also skip things. So I want to a little bit also know what you are most interested in, because if you download the files I uploaded and you got an email, you could in principle, we could always jump to another point to, and that we not, reach the laminar stuff, which is of course the most exciting one. So the first thing, if you have installed, so who has a Mac? First thing. Oh, almost all. Who has Windows? Easier probably.
Windows.
2, 3, yeah. So if you have Windows, you need to download this one little file .bin, right? This is just a kilobyte or so. It's very small. And then I can show you how you can import this in the edu world so that the intermediate files will work also on Windows. On Mac, it's not needed. I updated this last night, so they're all, or this morning, they're all files already integrated. So the first thing we can do, if you have installed Brain Voyager Edu, Windows in program files, Mac on applications, you simply double-click the Brain Voyager Edu. Maybe you have done this already. And then you get greeted by the program. In principle, we don't need this. You just close this window here. And then we are ready to open whatever we want for our analysis. Yeah. So the first thing, I think we look in the anatomical data, and then we can see how much we do. Because to run this, we need Python and TensorFlow, which is not so difficult to set up. But I can also run it on my computer, and then you can see how it looks like. And then we have not to use 20 minutes to install it and another 10 minutes to run it. So we can save that time. But you can open the same file I do. For example, you can open the Nifty file. Oh no, if you can, please open the file which I uploaded this morning, which is called, let me check how I named it for you. I think it is prepared anatomical files. I think this is the one. Please download this. If you do this, then we can also jump after the line can continue from there. So the Nifty file should, or the file there is a VMR file. I go here in this Layer-fMRI folder, and I have here two folders. One is I practiced or prepared the analysis, and then I have one practicing with the edu version, which we do now. And then I have just two folders, one for anatomical processing and one for functional processing. And now I go in the anatomical one. I think you have Nifty Anats and Nifty Bold, Nifty Vaso, and something like that. Since I showed yesterday some of the Vaso data, we work today with the Bold data. And if you have the time, we compare the laminar profiles across Bold and Vaso, which I did. Looks nice, really nice, like you expect.
So I missed one path, one subfolder.
This is just whatever you want. For me, this is just, I named it myself, layer cores or something, right?
So for with respect to the data that you sent this morning, this would be referring to the prepared anatomical.
Yeah.
Okay.
Exactly. The prepared anatomical, actually, you should unzip the prepared anatomical in your Nifty Anat folder. If you have downloaded the folder structure, then you should have a Nifty Anat, your NI files. Actually, we don't need them, actually, because we opened the downloaded files. And we are one step ahead. And I have them in this folder called anatomical preprocessing. And the one we load is actually named this one. So this is the one which is highlighted there. This one we should all load, called subdemo, amplitude rate, uni, dephased, reframe.
And
Yeah.
he's gonna open.
When I try to open it, it says that I cannot open with my edu version.
Yeah, then you have,
Windows, you need to download this bin file.
I've downloaded and after.
and then you have to import. I can show you this. Yeah,
Import it. I'll show it.
yeah, yeah.
So can you reopen the edu?
Question?
Can you close the edu version? And reopen the edu version.
Then you have not the latest Mac version downloaded, right?
Then,
You did?
Yes.
And have you installed it also?
Yes. This is exactly the word.
That's strange, I have to say.
Yes, but has the data done so?
So you want this space?
Did you remove it before you installed it?
Yes. Already.
Okay. Should actually work. If not, we can make it work, but let me just, because I have the same version on my computer.
So you would have.
So where's the data?
Maybe
Maybe you
make a copy of that file
can go
in your
there.
directory, and then they want to work on it. And so maybe you can just have an ask if they have in a folder.
Yeah.
Wonderful.
And then this one, yeah. Don't know why, strange.
Forget about
Okay, no problem. We can still use that data. Do you have also downloaded this zip file, this file bin zip? There's a small file. Yeah. Let me go there. Yeah. So I show you something now here. You can go here and say, add more data sets. When we browse to this bin file, maybe you can do that.
Like volumetric. I mean
A downloaded file.
so this is the.
Rainer?
All of the.
Unzip the file.
Can you go back?
This is data files.
There's one more file. One is missing.
I download this one. Yeah. So
Yeah, this had you installed, right? But then there is this one here. Bin zip. See this one? It's a very tiny file. It's 1 kilobyte. This is for.
Yeah.
No, you can also use on the Mac. Since your Mac does not accept this file, you can also do this on the Mac. Right? Yeah, this we unzip. Up.
I've already done it.
Oh.
So I'll show it. Okay, somebody has a problem, I can show.
But it's still there, should be fine. So now when we go back here, we just go on downloads, where you have downloaded it. Here, no, this is not the file. Maybe you can.
Okay, thank you very much.
Yes, it has worked. I can explain how people on Windows, anybody on Windows that has any issues?
Mhm.
I'm on Mac and
Mac, Mac, you have issues, that cannot be. It's a blasphemy to say on Mac I have issues, right, Rainer?
That's true.
It's a bit file, right?
You need
I
the,
tried to load it and it didn't.
We have
work,
to-
so-
yeah, so I'm gonna close this again because it happens when you open. So if you restart from Voyager Edu,
It's not opening in mine either.
Remote access, so it's.
I come to you in a second. So just restart it, and then in this initial thing that pops up, then down here there is add more data sets, and then you browse to the place where you've extracted this bin file.
And then let me just open document. and-
No. First you need to do something. So go to that place.
Yeah.
Yeah. So then you don't see it, but you do like the Windows style thing. So you do.
Just take-
Clusters. How do you do the?
No.
No. Then you take it and then you say import and then just as okay. And then that's it. And now you can open the files. It's a bit of a trick, but where are the files? That
In DE.
spoke? You don't see the bin file because nobody is on Mac. I'm coming to you in a second. That
Let's try this.
should work now. Just check
And
that
now
you
the-
load
Yeah.
The
This one.
CMRR file, yeah, just load one of them. There you go.
Right.
Okay,
Yeah.
so you open the
Rename it to
version
X,
and
to
before
this
you-
name here, the bin under. Rename it to edu, but you should put it Mac.
Yeah.
Yeah.
Okay, sure, yeah, okay. Oh, show it online. That's really funny. So it's actually super easy to do it. Maybe we have to rename on the Mac the file, but otherwise it's fine. So the idea is, if you're on the edu version, you can go in File and say, show edu datasets, just to get the front screen again, the welcome screen. You have this. And then there is a button here called Add More Datasets. If you click this, you can browse to this bin file and basically select it, and it should open. If the file cannot be selected,
Asterisk dot asterisk.
asterisk, or you rename it to edu_x dot because it looks for exactly that name. edu_x dot.
But if you search it for asterisk
Yeah,
dot asterisk,
that's actually
then-
better. Yeah.
Then you don't have to rename your files.
Where is that bin file? Sorry.
So we have downloaded somewhere. I have it on my computer in another place because it will. Yeah.
Didn't download the.
I just said download from the email. Send this
But you
morning.
don't need to. Also Mac.
Oh, the
you
one
do
that
have
is
to
under
be-
the window.
Yeah, probably not the. I'm not sure why. Something went maybe wrong. I don't know.
And then you download the link.
Is it part of the package that you?
No, it's part of the download links I sent you. It's 1 kilobyte. It's a very tiny file. It's an email called ending with .bin.zip.
Yeah, the one that you showed under the, for Windows do this,
Yeah,
there's the
just
bin
check.
file.
Yeah.
That's the one.
You have it?
If I have it, yes, I'll grab it and put it into Brain Monitor. I think, and then.
Then you need to unzip it first.
Thank you.
Yeah.
Yeah, otherwise nothing happens.
Yeah, and then go to.
Yeah, then you go to.
That's okay. Just say okay.
Then you go to the bunch. Then there are two, then you can do here, yeah.
Is it
Browse.
open?
Yeah.
Sorry.
Now you more. Yeah, successful. Yeah. This one.
There's my thing.
Yeah.
And then.
You just need to go to that folder in the
Yeah.
in the thingy of Greenwatcher, you need to go to that folder.
Not here in the program. This is in the program, right?
So you go like that. And because otherwise it will lost. Yeah, so you don't, it's not visible.
And that's what I meant before.
Because.
It's easy. Just go to this folder and rename it to.
Okay.
To show you how to rename it here.
Yes, thank you.
Yeah, what I'm saying.
Okay.
So, okay. Once it does,
Yeah, it looks too specific. This name here, this one. Rename it like this, and it works for sure.
Bin file?
the
The bin file, rename it like edu_x.bin. edu_x.bin, like written
For
here.
those of you that are on Windows, this is not for Mac, it seems.
It's only for Mac.
Why do you?
Mac is more picky.
Because so it's basically an extension of the license. It looks for a file that has a specific.
And does it need to be saved at a particular place?
And,
or-
No,
in
it
Windows,
saves it in the place I have here actually
then
open,
it lists
so-called
Mac file.
library application support folder, but automatic. You browse it, just say import, that's all.
Okay. Mac.
So if you have this file, yeah, good.
Yes, and just rename.
And just press import if you have browsed it, and then it should be fine.
Any Mac users struggling with that?
ex dot B.
Yes. I have now.
Then
Yeah.
here you go to benefits.
Then you should be able to open this file.
Now you can take it and
Just
then
here's the name here on top.
then it says okay, and then you close, and then now you can open all the files that are not the need.
Can you all open now this file?
Yeah.
Super. Perfect.
There you can
So this is the MP2 Rage Nifty file, which was included for download. And it's basically defaced. The only thing is done that it's defaced, right? So it's not recognizable which person that is. For example, in BrainVoyager, when you right-click and say here, volume render, it looks a bit strange, but you would recognize the person. Actually, you can make it transparent. We will not recognize the person because it's defaced, but you could, in principle, if it wouldn't be defaced, even with the noise in the background, which we remove, you could recognize the person. In that sense, it's important for sharing data, of course, and in any case, to deface data sets. That's actually all. We could now go to the deep neural network segmentation, which I showed you yesterday. Was wrong. So in volumes, there is here a menu, and it says DNN segmentation. If you click on this, it will first complain, as I said yesterday. It says, oh, this data is not 0.7 as it's trained on the neural net. And it asks to rescale the data from 0.75 to 0.7. But I wouldn't do that because that would mean, because 7 is so close to 7, it will work. So we don't rescale the data, don't touch it. And then you say no. And then you go to VMR properties. This is, do you see this guy here, such a panel with some short commands? Then you go there to VMR properties, which is properties of the loaded file. So what the dimensions are and so on. And there we just pretend for the moment that we have 0.7. So we lie to the program for a moment and say 0.7, 0.7, 0.7. We undo this later on. And then if I now go in the same dialog, it is fine.
Something funny.
File, and document. And then
When I don't have GPUs,
I have something
it
else.
still runs on CPUs, but
Yes,
it's longer.
it will run on whatever you have. The problem is only you have to install a mini Conda environment with the right TensorFlow and the right Python. And this I don't want to install now. We can. There's a link. Actually, we could do this. If someone really wants to use it, there's one link you have to follow, and it's a matter of 5 minutes and everything works. If you have problems, of course, it can be longer. And normally, I think because some will be ready in 5 minutes, some in 20 minutes, and that's a bit of a
So
problem.
do you have like a environment YML of something that you can just list all the packages?
Yes, in principle, yes. Yes. Yeah. But I would say I run it on my computer, but because I have Python installed.
Okay.
Actually, I will show you this for a moment that you see how this is in BrainVoyager. So when I go here in Python and say select Python, BrainVoyager lists all the Pythons it finds on my computer. You see? So you can actually use a Python you have on your computer, but it must be a specific version and it must have specific packages installed, right? And since I do not want to mess up with that, we don't do this now, right? So I cancel that. But just that you see what that means, because when you have Python on your computer, you can, for example, go to BV Notebooks, and you basically get notebooks which you can run most of the things we do today also from a notebook, right? Or from an editor. So BrainVoyager has also these coding capabilities. It's just that we do today everything graphically, just to keep it easy, right? But you can also code if people like to code. But I will not also do this today, just that you know that this is possible. And now we go into, I run it on my computer now and then explain some other things in the meantime. So I go in my computer to this DNN segmentation, and you should see the same thing. But I say go now because everything is prepared correctly, because MP2 Rage is set, not MP Rage, and slow means the best possible quality of segmentation. And that's our course data. So I say now go, and we'll first, as I said yesterday, prepare the Python code for this data, and then sends everything through the deep neural net. And you see then here a Python window. Actually, now it's a bit buried. You don't see much because it's here behind this guy. Let me make this larger. You see, this is the progress, right? So it's already working. In Python, BrainWatcher has embedded Python, runs through that, and then basically now runs it through the deep neural net. And you see, it will take some time, 20 times as much as now passed, then we are done.
I have a question about this.
And you can load, question?
Yeah, more not practical, but in the sense, does it segment each patch independently, or does it also take into account the relative positions of the patches?
Independently. So it has, as I said yesterday, the 64 by 64 by 64 cubes, the data, and goes through these cubes and sends each one. So for each voxel, it has the local neighborhood, right? But not outside the cube,
Okay.
right? In that sense, each cube is independently segmented. Yeah. But I show you now how you can actually go to the output yourself if you have downloaded the corresponding. So there are two ways now we can proceed. One is we go right after the deep neural net and continue from there, which I think we should do, or we go even a step further until everything is further post-processed. What do you want to do? You want to see the output of this and work with this? I think that's best. Yeah. Okay, then basically you just have to load one of the files you had to download, namely the, let me see what the name was of that file. This BMP here, this is the tissue probabilities, right? This will be the output of this deep neural net. And if you have downloaded this file, this is a few hundred megabytes, then you can just open it. I'll show you how. Did you download this file? Okay.
Yeah, no, I think if you want to do it, it takes a bit of time. You need to look online for the specific ways to do it. But it is not, so it will see it, but we need to locate it and do it right. So I would recommend you, if you have Python installed now already and it's working, not to do it right now, because if you mess up something, then your Python will. Normally, the right way to do it is that you create a new environment. So you create a BV specific environment for the packages that are there, because if you just add something and something goes wrong, then it messes up your Python installation. So I would recommend you not to run, because all you need it for is the DNN, and it's just gonna run for like 20 minutes.
I think it's really worth it if you want to use BrainWatcher for more segmentations, then you should install it at your place, but not now, because it's for this course, its installation can go wrong, and therefore it's not worth it. But there's a very, very clear description how to do it, right? I can send you that link. But first I want to show you, you can now go ahead of my computer, because you can keep your file, which you have loaded. And let me just go to the same file, because I opened the second version now. And basically open the same file you have open, this one here. And now, if you go to this panel here, there is something called volume maps. If you go on this volume maps, you get a dialog where you can load statistical or other kinds of maps and overlay them. For example, you say load, and then you can load the downloaded file. Prop slow, this is this one here. This is the file which will be spit out by the tool.
Then you have.
And if you open it, you should see something like this. And you can then select any tissue type you want. For example, now I have gray matter.
BMP.
Sorry.
Problem?
This PF, I found it. This was
Volume maps? That's, yeah, load. Then the downloaded file is not in this folder. Yeah, exactly right. So now you can, for example, select here any tissue. This is the labeling from the neural net, right?
So if I get follow up to Rohit's question, if it's working with patches, it means that I can actually also give it a slab. Right?
Yeah.
That's
Yes.
That's as well.
But I should say this works on MP2H quality data, not on the API or data. Why does it might work with the T1 rating? I have never tried. But just to be clear, it's trained on MP2H, 0.7 data. You know, just yeah. So don't expect too much. But sometimes things work unexpectedly. So it would be nice to try. Like you interpolate your SLAP to 0.7 and feed the SLAP, and it should in principle really work.
I mean, you could equalize the histogram from your mean Vaso to your MP2 range.
Yeah.
I was thinking of a slide MP2H.
Yeah.
Oh yeah, that should also work.
So now I want to show you a trick, a little trick. You see, this is the segmentation, but it's really in the space of probabilities. For example, when I say here threshold 0, here is a threshold. You see threshold min 0.1. If you just say 0, you get this, right? Because when you now threshold it with 0. If you threshold this with 0.5, you get the most typical gray matter the software can find, you know, which is more or less the same. So it says, I'm pretty sure this is all gray matter, which I have labeled here, right? So it's the probability, you say. And that's actually nice, because if you understand that, you can then also influence how multiple tissue types are combined. But we will not do this today. So here's the white matter, gray matter. Go back to the default of 0.1. So now comes a trick. Important thing to know. It's nice to show more than one tissue type. If you click, you always get the one you click. You go in advanced in this volume maps thing, click on the advanced tab here, and then you just say multiple selection. Then you go back to browse, and now you can add, for example, here white and gray matter, or any other tissue type you're interested in, like blood vessels. You can try out this, you know. Actually, when you want to see this a bit nicer, you can either zoom in one of the slices like this, right? And you see a bit more. And a nicer feature we use for the layerification, for the drawing of our eyes, is actually you use your Alt key down and then draw a little thing, and then it zooms in, right? You can use this, for example.
So, Mac is command,
Alt,
right?
it's also Alt.
Alt. Can I ask you a question?
Yes.
I shouldn't ask questions because I think I know the answer. But when you create the final gray matter, let's say binary for layerification, do you use maximum probability to decide whether it's gray matter, white matter, or?
I come to this just in a sec. This is the post-processing I just want to discuss. Ask the question when it's
okay.
Okay. Actually, this is the next thing I wanted to show anyways. It's a good question. Let me just so since you can nicely zoom in here, you see also, and that's related to your question, the transition zones. For example, this is color mix between white and gray matter. So these are the fringe voxels, right? And you can influence whether you want to have a bit more towards CSF or towards white matter, your gray matter, or whether you do the opposite, right? And in that sense, you can influence how you discretize this. I mean, if people want, they can also work with probability. There are many tools also using probabilities for segmentation, so you could also keep that.
What's Alt?
Alt is called, is control. Sorry, you were right. So sorry, and the Mac is control. It's the second from the left in my computer. The third, sorry. Shit. Option. No, control. No, it's not command. I don't look at the keyboard when I type. No, it's option, sorry. It's for sure option. It's for sure option. Sorry. Because I don't look, I just have it in the fingers. Option. No command. Option, draw. What? Can I try?
Yes.
Can I just try? Oh, yeah, let's see. This button.
I do. No, you see option. Try to do option.
What?
Yeah.
You need the
Just try it twice. Try it twice. Do you get the zooming? Good.
good thing of this view is that you can actually draw in this view. And it will
We'll
affect.
come to this later when we do the. I would now come to your question, Federico, because what we now do is we open the dialog which automatically opens the tool when it's finished. You see, I have now two EDUs here. I go to the one which calculates. It's done already. You see, it came up. This is now the EDU version which I run before, and you see it's the same segmentation we got, but it opens already this dialog here, which is the next post-processing. And this dialog you can now also open because we have just not done this, but we have opened the tissue file, and basically what we can do, we can here on our computer go to volumes and say DNN segmentation post-processing. If you click this, you get exactly the same dialog which the DNN tool at the end opened up automatically. Okay? And then we are exactly there. So if you would have Python, you would all be at that point without having to load this file. The file would be created by this tool. So now comes Federico's question, and there's a new options. You haven't seen Federico, they're new. There are actually two ways to convert. So normally I don't change it except I see, oh, there's really a bias, right? In this data, there's, in my opinion, no bias. You can just click convert. We can do this in a moment. But just to explain, we have these possibilities to boost white matter over gray matter. That means white matter will, the transitory voxels, white matter will get them. And it sets the probability higher than it is to win against in the transitory zone, right? But we will not do this. And the second one actually uses absolute thresholding, which sometimes is better. But I have a document what you can do in which kind of biases. But normally there is not a big bias. But it's good to know that you can influence this. So you don't have to do anything. You just say convert. And then very quickly, you have now, it looks more or less the same as before. But it's not, because now you have discrete voxelations, right? So there are a few errors here which automatically will be removed by the post-processing. But you see here, this looks like, oh, this is the same we had before, but it's not, because now these are discrete, exclusive, that means non-overlapping, discrete tissue classes. Here's also white and gray matter. Oops, sorry, this guy I close. And just to show this, if I turn, so I should tell you, do you all have this dialog called volumes of interest, voice? Do you all have this? So if you click on an item with command, you can add more and can turn off by repeatedly clicking them. But what I want to show is that if I turn them off here, so I just command, in the Mac it's command click these guys, then it's off. But now if I go to the volume map, which might be still open, or if not, you can open it. If I now click here on for example, white matter, this is from the probabilistic overlay, and this one here is from the discrete ones. You know, they now overlap. You see? Probabilistic, discrete. And here you can check whether your conversion works or not. Right? You can check for yourself whether you like the result or not. I think it's pretty good. You can also here, have now the white matter from probabilistic thresholded map, and I add the discrete gray matter on top of this. So it's a bit complex because you have two different representations. One is a probability, like a statistical map, right? Like a thresholding thing. These are the tissue probabilities. The other thing are regions of interest. No, they're just either I'm there or not at this voxel. This binarized. So in principle, we do not need this volume map anymore. You can actually close it. You can even, if you want, delete everything, but I would keep it for the moment still open. And go back to this post-processing dialog here. We had clicked the convert. We are done with that. But now we can either say run all, or we just want to see what it's doing. For example, here's a clean step. It says remove non-brain voxels. So let's remove them. I click on clean. And now it runs something and has removed some some voxels outside the brain. You see still the noise is still there, but not tissue labels outside, like gray matter or so. Then I say remove cerebellum from subcortical voice. So I click, you see we have here the cerebellum included. How do you remove the cerebellum? If you click on remove, it will actually bring your data quickly in MNI space. Sucks, goes there. In MNI space, we know a template where the cerebellum is, adjust it a bit, and bring it back into our space, and then it's gone. Right? So now if you go back and look here at the white matter, gray matter, you see there is no cerebellum anymore marked. It's gone. So these are the steps the post-processing is doing. The next one is disconnect. So it separates the two hemispheres, left and right. I press disconnect. And now it separates the left from the right hemisphere. Although the brain is quite oblique, right? So it's rotated. How can we validate this? You see here, I now have new white and gray matter for the different hemispheres, right? For example, this here is the gray matter on the left, and I add to this the white matter on the right. That means I have the two tissue segmentations separated for the left and the right hemisphere. So you can now create meshes. This comes next for the hemispheres. So then it creates some VMRs. Since you do it, you not even need all the files you downloaded because they were only done if you wouldn't do these steps, right? So I now say create VMRs. Then it does some segmented VMRs from the tissue labels. We look at them in a moment. And then I say the last thing, create surfaces from the hemispheres, white and gray matter. So that's happening now. Just move a bit away. So here, for example, you see the gray matter surface. It's this one. And if you go in meshes, go load, you find also for the left and for the right hemisphere, LH Rico smooth. This means it's a bit smoothed without shrinking. It's a very nice smoothing kernel. And then you basically open this and you see here the white matter, right? From this segmentation. You can also open or add actually, if you have a Mac, you can use the pad to nicely move and rotate this guy. On the Mac, this is really nice. That is all. This is completed. This is the DNA segmentation and the post-processing. Right?
Can I ask you a question?
Yes.
In the old days of Brainwatcher, on a segmentation, we would always run topological correction.
You don't
do this anymore?
No. I mean, you can, no problem. Because it's a good question, because the old files are done now differently, right? But they are still there. If you go open and say, I want to see what we usually in the old days do, this guy, it's still there. You can run the topological correction, no problem.
But then you would have to combine the topologically corrected white matter with so in order to then get an exclusive connection with the gray matter, right? You have to somewhat write some code, right? Because now the voxels are correct, you either have to remove or add from gray matter accordingly.
What you can also do is you correct those and run it through the advanced segmentation, which I mentioned yesterday. You can still do that. It does these things then for you. But you start with the DNN segmented white matter and then let it do its other job.
Those of you that don't know, I mean, segmentations often have these topological errors. Like if you look at the surface, it looks like you have a donut, so it goes through. And Brainwatcher has a very nice algorithm that was written actually by Rainer together with Nico Kriegeskorte when he was doing his PhD with Rainer. And the nice thing of that is that it corrects these errors automatically. So it really applies these corrections in a way that you do not get these errors. And if you work on surfaces, doing that is important because if you want to then, for example, create a sphere.
But you see here, Federico, here in the back.
There is some, right? Yeah.
A little bit, but the quality from this DNN is here's a little one. See this one?
Yeah.
An MCG,
Yeah, and you can correct these things, but honestly, you can inflate that, it will work.
Yeah.
So normally, these are good enough for, except you really go to cortex-based alignment, then you would need to do that. Yeah. Okay, so now I want that you open one file which it also saves, which is called reframed_brain, which is one where it adds the real tissue values, the intensity values, I mean. And this is one we continue working now, and also had made this available. So this has this name, reframed, and then brain.
You just go.
Just open it, it will be there because it's generated by your computer by this tool. And what it is, it's basically the segmented intensity file, right? So it's not now a segmented file or something, but it's really the real data, so to say, but now segmented. You have it, Rendo? Good. This file we will now use as a bridge to go to the 0.3 space, because we can interpolate this to from 0. Oh, now I caught myself. Actually, you should go back and tell the program that this is not 0.7, but 0.75. And how you do this, you can go in BMR properties like before, and it will say this is 0.7. And we did this just to run the tool without any issues, because it would also work without doing anything. It would just rescale it to 0.7, right? But now we know in reality it's 0.75. 0.7, sorry. No, what did we have? We had 0.75. Then I did this already. This is on my computer. But you have to do this.
So
No, because they didn't run the DNF. So.
we loaded your.
And then it's for you already 0.75? Good, good. Because I wasn't sure that I forget to tell you, so that you have it already. Good. Okay, then let's do the following. We now combine two interpolations into one. So the first is we upscale this guy to 0.3. So if you find this guy, there is actually this where do I have this? I lost the panel. Doesn't matter. You can always right click here, then you get the same panel. It's just that people didn't know, and I wanted to have them make this visible. But so if you go here in the so-called 3D volume tools, which is this window here, you can say full dialog, and it expands. It looks like this. And then you find here things like co-registration we come to later. But now we go to spatial transformation. And we say we want to scale or isovoxel, actually not actually needed isovoxel, but we go in this one here. And now we tell the software, do this, go from 0.757. Oh, here's, I forgot, made a mistake, probably because I was before starting to do it. Let me just quickly go back. BMR properties, and I should tell this guy, yeah, I deleted this in my computer just now. No problem. So then you go in this isovoxel, and you see on top, the voxel at the moment the resolution is 0.75, but we now go to 0.3, just to be ready. So with the data, you could then also use Laney at the end. And I start to like this resolution. Normally, I recommend 0.5. And I know Laney wants 0.1 to 0.3 or something. So I'm in the edge for Laney, but it's still okay, I think, 0.3. Seems to work, but I tried at least. And then we say, then we go here, then we go to this space, 512. and rest we can just keep. If you go then here, it will spit out this file isovoxel to 0.3 millimeter. But it will not fit entirely in the space, should have used a larger space. You can say how big should be the volume you squeeze that brain in, right? So what we do, actually, to make it simple, there is actually, I first oriented it in axial ACPC space, and then I think I did not. Here. Oh, no. Just a second. So this is our file. And then we do it a bit faster by load transformation. And there you find a file, which was also in the download files, which ends with combined ACPC ISO 0.3, just to make it a bit simpler. You have this file?
How did I get the load transformation?
So you need
Yes, load TRF, load transformation
in
is,
the volume.
yes,
3D volume 2's
co-registration, I think, or spatial transformation.
spatial transformation. There should be
Exactly.
a lengthy
Then
load.
this combined, wait. You don't have it. Maybe you have to look in the downloads.
And it wasn't.
Let me have a look.
This was the downloads.
This is the one combined. This is the one.
Okay.
It's the one. Perfect. Yeah. And then you go in, when you have clicked this, you go in spatial transformation. So you go, let me do the same you did. I just open it. Then you say here, transform VMR. Click this button. Now we do two changes. One is we say 512. It will fit there, more or less. And then the other thing is, anything else? We say here, unknown, we say this will be a pseudo ACPC space, just oriented to ACPC. Then you say go.
Which file?
It should look like this. You see, now we have this actually not at AC. AC is here. This is the anterior commissure, right? So I made this on PC to just save a bit of space because I cut a bit of the front, but I moved it to PC as a center. Then the whole back of the brain, which is most important for us, is inside this, right? So more we don't have to do actually. Now we are ready and can start this functional processing and bring our data all in that space. That's the next thing to do. So we went from this, original oriented brain, now to one which is oriented nicely in orthogonal planes, right? And has a sampling resolution of 0. Actually, now, since we did a combined transform, it doesn't know the final resolution. So now we have to go in VMR transform and really change now 0.75 to 0.3. This is important. Just do this. 0.3.
You did do the.
And then simply save. If you go here on top, there is a save icon. Just click once and save to be sure this is now with the new value saved. 0.3. So when everyone is at that point, we will go and work on the functional data. We could here do a bit more things, but I think it's better to move on. I want to show a bit of the functional processing, and then we look at the laminar stuff. How much time we have? I forgot.
We have until 11, right? 1.5 hours.
Oh, that's good. That's good.
Can we maybe wait 1 second?
Yes.
Have people catch up on this because some people didn't manage to do the steps. So I'm
Good,
gonna have
yes.
1 second.
There are all the in-between files as well. Like the brain is there already and the transform. I can.
No, she doesn't have it.
Okay, who is not there yet?
Yeah, it's a tablet, so it takes even to open.
They're quite big files. I hope your tablet managed.
Remarkable that it's running.
Huh?
I mean, it's running on the tablet.
That's good,
Like a
actually.
Surface Pro.
That's nice. Yeah. The memory might be a problem for some steps.
The combine. Oh yes, that's one.
Why does it need you? So this is big steps. And then what you have to do is these steps that come out. But
I just repeated what I had done. I had the same issue before. I think I applied the same transformation twice, maybe. Or I loaded it twice. I don't know. I had kind of a really zoomed in. So I just reloaded the brain that was prepared and then applied the transform.
Yeah, that makes sense. I think I ran into the same issue.
Oh yes, yes, okay. So let's the brain. And then go to transform and find the transform and so. And give it a second. There you go. Oh, yeah.
it's incredible. It's running on
Sorry? Tablet. On a tablet. Cool. Yes.
done some magic. She does even the MRI conversion on the tablet.
Yes.
Did you know? Sync interpolation on the tablet.
Yes. Not bad.
Yes. And then
You can also let it define Q, but for some, if you, for example, align data, it's sometimes good. It knows the center is always the middle. So you can have any cube as long as the center stays the same, right? Within the cube.
Well, why does it need to be a cube though?
There's historical reasons. It's not really important. I will also remove this at some point.
okay.
Sometimes it's good.
Well, then you have one file and then you use the transformation file and you can go to
Sometimes you need only a part.
space.
Don't want to have
Face where Liner has a high.
And then sometimes you can make this
The
like I
concept
did.
just to understand.
No, but I just do
But yes,
not in the battery safe.
I will at least have not calculate yourself.
Otherwise,
No, and you have not to think.
okay, but after that, it's fine.
Laziness.
It's
Always more challenging things. But I'm now
the same thing.
this remarkable doing.
You didn't reload your brain.
Then what you can do is you can evaporate everything back to 0.3.
You just see it. Yep. Yeah.
I was doing load transformation.
Yeah.
And something happened, but the name of the file is different.
Yeah. And then once you have done that, then you should have a PRF file. So you need to open this brain file, not the 0.3, but the original. That's the one you have created now. This is this one. But I think what you have to do is to open.
So if I want to run the tiramisu on different data,
Yeah.
what I would need to do is have, I guess, 10 brains with training data and then approach you and ask you.
No. You don't have. You can. The nice thing is it's all open source. So in this version, you can just copy the Python code, use Goebel, which I call it anyways, change one script called inference, and just put in a script or put it by hand. Your files in, and it just works. You don't have to do anything. But if you want to train it on some new stuff, it's also there. You can train the network with new data too. Yeah.
And how many have ground truth data did you have for training when you trained it the first time?
Marian did, I think,
Then it opens a new
and Baruch,
file,
Then it will open automatically the new file after the
maybe 8.
installation.
Not many.
But
But of
you
course,
have
since
a
it
file that-
partitions it in subcubes, they're always new data. So it's trained because it's based on the 64 on hundreds of data sets,
Exactly.
which are these cubes. It's a trick actually to give without augmenting. That means inventing fake data. You have real data, but a lot
Then you go back
because of the
original
cubes.
file, you put all the transformations together, and then you apply them in one block.
My screen to give more space
Mhm.
and the thing crashed.
Hmm.
So if I do file,
Okay, now if you close,
Yes, and
there are some of the files.
yes, perfect.
This is the one we want to.
That's the one we look at later.
Yeah.
No, it's the one. Actually, just open it.
it does all the steps for you without basically you be able
No.
to see
I think you forgot to say 512 because now it's in a very small box. I show you how to correct this. Go open
I
again.
think Rainer makes all the
And,
commands one after the other available,
open
and then you call
the-
the commands.
The
And then
one
Calling the
brain,
commands
called
one after
brain,
the other is like
brain.
the same thing as
Not this one.
clicking run all. And then, okay, so now it's done.
This one, exactly right.
Uh,
This one. And now go in,
yes.
Did it work?
make this large, the
No,
button
that's
full.
Okay, for me, it was like half a second or so.
Yeah.
In the sense.
Maybe you, it's
I
sometimes.
think you did this before. I see. Go to spatial on the next one. Load TF. And you had the right file. Yes, this one. Perfect. And then go to spatial transformation, transform BMR, correct? And now you say 512.
This file
The
that.
rest you can leave. Yes, and then say ACPC and go. Now it should look better.
This file now is 2.3. So it's 300 microns, 300 micron BMR. And it's in a space where the brain is a bit more straight.
Like the origin of the image is
The origin of the image is the anterior connection.
The center is not in PC.
That's what I was expecting too.
Mm.
And I think for the VM.
So.
You can also load this file or a similar one prepared just for now. No, I don't know why that happens. Maybe you go to open
Actually, that's what.
and one of the prepared files.
Does.
Are here the prepared files? Yes.
Yes, but it's also saving the new ones that I'm creating. Or saving
Maybe you unzip it again
Okay.
because that file is there.
Yeah.
And then we can later, maybe after in the break,
Yeah.
I can have because now I have no clue why it's not.
Okay.
Yeah.
Yeah. Okay.
Sorry. Yeah. Hmm?
Is there a reason you package the DNN as still like TensorFlow models and not like a binary that can run, that can be deployed?
So the good thing is that you can. Before
I mean, I normally in the TensorFlow world, people give you the Python code, right? And you just in the whole AI community, people mainly use Python. So that's actually what the people want usually. Right? In BrainWatch, it is like an executor because you don't have to touch Python. It just does it for you. Right?
Okay.
And you could wrap it yourself with a little exe, which is 10 lines of code. Right? So it's simple. But normally people want the Python. Yeah.
Because it's flexible in that.
Exactly. Exactly.
Stop up. And then before Rainer was putting ants inside, I was putting ants for the things where I.
So now,
Yes. Some
So I opened one out.
this is the next stage. We don't do it now, do it later, but you can just click. This one should be this. Oh, this is TF. You're right. No, then use this. It will be looking a bit more clean because it's then white matter clean, discretized. But otherwise, it's the same file. Yes.
Yes, so then.
Don't think you can give you everything, and I think one good thing would be to adapt it. So this is something.
So now you can just close all your VMRs, which might be open. And I think you had a good impression how this DNN works and that you can post-process it. And now we upscaled it to 0.3 millimeter. But now we go to the functional data. And there you can open, we work with the bold data now. And you can open in the nifty bold folder, open run 3. We will ignore run 1 and run 2. And I will anyway show you how we average 4 runs. But at the moment, we just load run 3. So in my computer, this is a different folder name. Sorry for that. It should be nifty bold in your case. And then you should find your 6 runs. Actually, I already.
We clear this is the original data that we already downloaded. This is not from this morning.
Yeah, original data. This has not to be, yeah, you can just use the data, yeah, which you had originally earlier downloaded, not today, because it hasn't changed. Actually, here I have a similar folders like you. Here is, in my case, it's called all runs bold, all runs way. So here, all runs bold. And I have already pre-processed them. We will do this in a moment. So what you should find is sub demo run 01 underscore bold nifty. And you just double click it, and you get this file, and it will open it, and you are done already. It will automatically save also a so-called Brainwatcher-fMR file, functional file. But I have the nifties not downloaded again. So I had just opened this file. So this is how the first run looks like when you open it in Brainwatcher. And you get a mosaic layout of all the slices. And you get the information about the resolution, 0.796 or 0.8 in principle in plane, and 0.8 in depth, right, in the thickness. And then we also see the TR is here 3.688 seconds. Here it's just shown in milliseconds. This is verified because the Nifty header had this information. Brainwatcher says, okay, I trust Nifty, so it's okay. And yeah, the rest is not yet so important. But
may I ask, so you already loaded the fMR?
No. The Nifty will open this and saves an fMR for you automatically.
So I go to Open Nifty.
Yeah.
And look.
Open Nifty. Go to Open Nifty. You can use the icon or in the menu. Go in bold and open the not preprocessed. No, yeah, just to show people.
This is the answer.
Yeah, perfect. You just say open. You know what happens? It reads the Nifty. It takes a moment. There's the Nifty header, and there comes the. Just that takes a moment. This is the same now I have. You see? Yeah. And you have an additional thing. You have the Nifty header. So if you open the Nifty, you get one thing more than I have. You get, and I saw it in Renzo, you will of course also get Brainwatcher opens the Nifty header and shows you this tabulary that you can see it. This thing here, fMR properties, is something similar like the Nifty header, but it's more general. It also works for DICOM files and so on. So now in Brainwatcher, if you want to see a time course, you simply click somewhere. You get a time course. So you can now inspect all kinds of voxels. Maybe if you go to the visual cortex, you should see something nicer. You see, it's a lot of voxels. That's how they look like. So if you want to see a slice large, you just press the Command key on the Mac and probably the Control key on Windows, and then right-click. You get then a large zoomed-in version of these slices. And now, because we can make very quickly a statistic in Brainwatcher. For example, you go in analysis and say, actually, it's nicer to use this panel. If you have this panel here, then you just say single run GLM. Then you get such a dialog. If you go, this is from the Nifty file because there was a TSV file, a tab separated value file, which had the protocol which you sent me, right? And I exported this in Brainwatcher back into a bits compatible file, right? So if you now go here and say define predictors, you should see this. This is the hemodynamic convolution of the checkerboard. You see now the convolved time course, the prediction of the ideal response. And then you just say go, and wait a moment, and you see your statistics. You see here, for example, I see these red things there. These are, and if you want now to see not just a single voxel, you drag, don't press Alt, just use your mouse and drag a region and let the mouse go, and zap, you see then the activity from the region you have dragged. And what you see on the left side, which flickers around, is basically the beta. You know, it shows you when you go with your mouse over it. You just zoom a bit in. So if I now here with the mouse go over any voxel, here the beta is 11. It's huge, right? Actually, it's percent signal change because I convert this automatically. You can change that, whatever you want to see. But now I do percent signal change. It's huge. So of course, checkerboard visual stimuli, they are really strong.
But you're saying that this is on the motion uncorrected data.
Exactly. Already at the motion uncorrected data, no high pass filter, it already looks that good. And that's because you have, and it's just one run, right? Because you have so strong, given us so strong data, Renzo. It's fun because one run is kind of enough. Maybe not for Basel, but still, one for Goebel is enough for this paradigm. And then you see here, for example, if you go here in early visual cortex, you see we have not corrected trends and drifts. We will do this next. That's the exercise we do now, right? We pre-process it. We do motion correction. And now I show you the tool which I showed you yesterday. So if you go into analysis, and then you go in a new button, which is just the third from the top, prepare a cross-run motion correction, right? Then you have this new tool. And now what you say is you can actually use a mask file. We don't do this. We go in here. How do you get all 6 runs in there? You just go on the left upper side. It says how many runs you have. You just say 3, 4, 5, 6, and then you have 6 rows. Okay? And then you say here, give me the first run, because we can also have the third if you want. Maybe we do only 4, but then you see not much. Just use all runs to see how big the motion is in the first 2 runs, right? Across the 2 runs, I should say, not within the runs. So then you use your unprocessed files because you first have to open them all, because you have to give not nifties at that point, but the fMR files, which is the same as the nifty, but just in BrainWatcher's way. So therefore, you open the nifty file run 1, run 2, run 3, run 4, run 5, run 6. You could script that, but it's just for now, do it by graphics, okay?
I don't know where the nifty parts are. Is it something that?
They're in the nifty bold folder, nifty bold. They are the.
I think they are not in the email. They are in some place.
No, they are already earlier. Email was only an update.
I missed one part. How do you go from mosaic to this big view?
You just
Command the left mouse. Right.
command right click.
Right.
Okay.
On the slides you want to have enlarged. You know, you right click with a command down or control. Oh, this snack.
Yeah.
Oh, it's a nice small one. Yeah. And then you hold the command key.
Yeah.
And then you go here and make 2 finger.
Oh, yeah.
Whoops.
Right.
Same way you can go back. And you can also, it's actually nice to know, you can also just browse through. So if you click inside, oh, I just moved this guy on this slide, and then, yeah, right, left. See, you can go through the slides.
If you want to show them the motion of one run, I think it's nice to also show.
Comes. No, I first want to show them the new tool because we do it before. We do it before to plan, and then we look at the runs. Yeah. That's why I want that you open all 6 runs, even if we later on average run 3 to 6 and work with that, because it's the same protocol. We can just average them. And this I had also prepared one of the downloads.
Open all the files. Did you open all the nifty files? Okay. You need to first open all the nifty files such that BrainWatcher converts them to
Exactly.
What run? In BrainWatcher, like there is this download. Not from this morning, like.
Oh.
That's all the information left.
Open all the different parts that are there, all the routes, and just open them in BrainWatcher like you open the first or the third. And create it in such a way that when BrainWatcher opens them, saves them as FMR. Then you can go to start, just to say if you.
For the data, I don't.
Oh, okay.
I have the zip file. But
So right now, the target one is the first one.
Yeah.
Yeah, that's right, then you wait.
No, that the point is, but the insight comes when you do the first one, because that's what people usually do. They say, my first one is my reference, second, third, fourth. Then we get this plot, which does not do motion correction. It just tells us, oh, you should maybe not use the first one. And this I want to repeat now. So just do 1, 2, 3, 4, 5, 6, like shown here.
Yeah.
If you have this, you can click go.
This is.
That's the new
That's a new thing. And you see also in the incremental mode, then it calculates this pairwise thing, which I explained, and then adds up the transformation.
Rainer?
Oh,
For example, if I have my own data in Nifty, so I think the FMR also uses the TSV that has the same file name, and then incorporates both to get the FMR.
Yeah.
So whenever I have my own experiment, I have a board Nifty.
You can always start with Nifty. The Edo version works best with Nifty. Yeah.
And then I also have a TSP right next to it in the same direction, the same depth.
Yeah.
Then it can automatically.
Yes, exactly right.
That makes sense.
Yes.
So BrainWatcher's Nifty supports bits. You can have a TSV, you can have a JSON sidecar file, it will include that, no stuff. If you have these 6 files, maybe some for exercise start with 3, 4, 5, 6, 1, 2, or 2, 1. But I start like 1, 6, and then see nothing. Ah, here it is. You see here on the left side. This is what I showed you actually yesterday. This is how it comes out in BrainWatcher, right? And you see exactly what I showed you yesterday. The big motion is within run and so to say across the first 3 runs, because there it accumulates these parameters you see. I showed the 3 translation, the 3 rotations, and RGB is X, Y, Z. It's also shown in the legend on top. So there's no X, no motion like this, X, but there is quite a bit of motion in Y, right? Across the runs, the first 2. So therefore, I would suggest to use run 3 as the reference, and you would then have to repeat this, because for the actual motion correction, you tell the program. But actually, we could also make, this is different than what I showed yesterday, we could also make now already a decision, because I have prepared the average of 4 runs in case we don't come to that point, pre-processed runs, and only averaged runs 3, 4, 5, 6 for the bold data. So that means what we could now just do is we give it 3, 4, 5, and 6, and just forget run 1 and run 2. Okay? And we have to do this, and the reason is we use these outputs it produces in a moment when we do the actual motion correction. This is just preparation. So what I do now is I go once more in this tool, prepare across run Moco, and then I tell them, now I have only 4 files. And my run 1, logical run 1 is run 3. So I give it now run 3, run 4, run 5, and run 6. This is the one we really will use.
So the reference volume now is still 1, which is.
No, we ignore run 1 and run 2, because we proceed only now with run 3, 4, 5, 6.
But in the interface, the reference volume will be volume 1. Here.
Yeah. This is actually what I have to finalize. This is a beta version. The ref volume cannot be changed at the moment. It's just 1. But in the released version, it will be changeable. But it's not so important because this is, you can change your reference one when you do the actual motion correction. It's just for preparation. And then usually the first volume is nicely T1, more T1 saturated. It's actually good to use the first one for this thing. It's not the actual motion correction. It's just a cross-run motion correction, the first volume, right? And if you go then to the fourth or so, or middle, it's usually less saturated. So normally the first are slightly better, but it doesn't matter too much, right? But you're right, if I align to run 4 later on, I could also use here run 4 just to be consistent. And that will be enabled.
Okay. I'm working on my computer in what axis? It's not in this one.
So if I now say go with these 4 runs, that's what we get. And now because it has more scale, you will see that the changes are actually very small. You should not be alarmed. Oh, there's a lot of motion between run 4, 3, 4, 5, 6. It's just that I adjust the scale to just show the difference, right? And you see, for example, the values go from 0.004 to 0.2, which is very tiny, right? Relatively tiny. Before it was much larger, it was several millimeter. But it not only creates these figures, it also saves the transformation files as SDMs, which you give now in the motion correction. Except for run 3, because run 3 is our reference. We just do motion correction like in classical brain motion without doing anything. And then we use the transformations it has calculated. These ones here, these are transformations we will use, which are here calculated. So if you want to run motion correction in run 1, you go to Analysis and press the first item in the menu. It's called fMRR data preprocessing. You can expand this dialog. And actually, this is a 3D readout. We do not use slice scan time correction. Just turn this off. Right? No slice scan time correction. We do high-pass filtering. I come to this in a second. But first for our motion correction. Here is an options button for motion correction. I press on this. And then you see here align to target run and then add transformation. This we will use in a moment, but not now. Because this is our reference run 3. We just run it without anything. And then later have run 4 linked to run 3. You know, run 3 is our reference run. You can also say here you want another reference volume. For example, I use now volume 4 as the reference. You can do this. And I can even skip the first 3 and say just ignore them. Right? And that now will be, it's also new, will be added, you see in the name, which is your reference volume and how many volumes you have skipped.
I think you're running it on run 5. I think you're running it on run 5.
Oh, is that true?
Something or
Ah, yeah, you're right. It's my bad eyes. It is also small here on my little computer. Thanks for telling me. Federico has good eyes. So we go to run 3. Not anymore. We go here. This is run 3, so I made yeah, this is better, true. I turn off slice scan time correction, expand this, go here in options, and say I want to have run reference volume 4. Just skip. I mean, in this data, it's not so important. In the basal data, it's actually good you go to reference volume 4 because the first ones are really a bit special. And that's, skip the first 3. That's all. You can also have a mask here, which I use for the data I talk about tomorrow. So, and what high-pass filter should we use? I think we use a Fourier in the GLM version and use 11 cycles because we have 12 repetitions, so this is safe. And then you say, just go. And now what you see is, this is the actual motion correction. And you see, we get also the frame-wise, this is also new, Federico. Have you seen this, frame-wise displacement? So you see here the frame-wise displacement, and you see on top the 6 translation rotation parameters. And you see there is still some motion in the y direction, but it's much smaller than what is in run 1 and run 2.
Why is that fast? The computer right?
Is mine faster than yours? No. Have an M4 Air, but it's an Air. It has no cooling.
I have, I think, M2.
Is this MacBook Pro?
It
Should be
is,
faster.
and I have the Max thing.
But you need to check which speed setting you're on.
But here now at the end, you see actually the corrected motion. Here you see,
Yeah.
you see here on top, although this is the good run, you have a bit of motion. You see this in run 3, but here you see it's pretty stable. It's just a bit of, and you see no much frame, but just noise, and that means it's pretty good removed, right? As you explained yesterday, there's always a bit of extra noise. And yeah, but now comes the point. We correct now so actually, before we continue, I want to show you now the difference in the statistics. So we have now run 3, and we repeat our GLN, and we can actually also add the motion parameters as confounds, right? Actually, I will not do this, but you can let's just do it. I add here and add the actually, you don't have to do this, but I can add the confound predictors, the motion predictors as confound predictors, right? So detected motion, which sometimes helps a bit. In this data, it's not really needed. I just do it here for fun. And then when you run the statistics, look at this, it's extremely strong now. So we can go here in the statistical map and add a bit of cluster thresholding. And you see how amazingly strong that data is. Now we have pre-processed, and you see lots of smaller active regions come active here, and even in the checkerboard, which is, if you have is still one run. But you see in this one run, you have lots of frontal activity in visual stimulation, which people often not report, right? Yeah, but not this guy here. This is not frontal life. This may be here. Yeah. But the point is you have a lot of posterior, look at and because now look at the difference. It's pre-processed. That means your time courses looks stationary much more, right? And now I show you something which is also nice for vaso. If you want to have time courses averaged, right? So what we do now is we go in analysis and say event-related averaging. And then you simply click here on the checkerboard and you see an idealized time course. And we use this to now look at our data and show the empirical time. This is the predicted time course, right? If we just save this file, create average, just take here the name it selects, doesn't matter. Then I can tell the program, do here an average. Oh, why we have 2? This is the idealized one. So now we can compare. You can compare the idealized time course, which is shown here, with the empirically observed one, and you find these 2 peaks. And so you talked about yesterday of these 2. You see this in the bold data, see? And this is the predicted idealized time course of averaging all 12 repetitions. This is this time course and all 12 average. You see, even in the single events, you see this double peak. Now, not in the sense of layer, the sense of early, late. You had this point. And you see, this is the empirical time course, and you can, the nice thing is, since this window, if you once have this event, and every window stays open, except if I do nonsense. And if you select now another region, you get it automatically drawn for the other region. Look. Actually, here actually it's a more normal time course, right? You have a bit of a peak at the beginning, and then it plateaus. It's more like bold typically looks like. So this other region looks more like the predicted bold. Sorry, yeah?
So the idealized time course seems to be changing quite a bit in scale between one region and the next, and I'm wondering why that.
No, the idealized is always set arbitrarily, just randomly. It's just to have some variability. So this
I
idealized.
care more about sort of the correlation as opposed to the actual size of the thing.
No, there is no.
No, it's just informative.
Yeah.
You know, actually, you can also remove this guy if you don't like it, because when you do the event everything, I just select random idealized time courses. But if you go here, ideal, see this ideal here? You can turn it off. Then you don't get this anymore. This is just your empirical data. Ideal, you can just remove. Because we have only one condition. If you would have now another condition, rest is not a condition, it's the only baseline we have, right? But if you would have checkerboard, flickering checkerboard, static checkerboard, moving checkerboard, or something else, faces, houses, you would have one line per condition in this plot, right? So this is pre-processed data. Is everyone at that point? Do you have this reached? You have the fMRR, you have done the motion correction and looked with event-related averaging at the time courses? So what we now do is we do the motion correction for the run 4, 5, and 6, which usually is nicely done by scripting, but I do it interactively because of the new tool, which is not yet scriptable. So I go in the fMRR data preprocessing. Oh, sorry, I first load this was run 3. This time I think I was correct. Yeah. And now I load run 4. Run 4.
I mean, a motion correction.
No, the prepared motion correction. So line 2 and 3. You run it like that, just runs run 4 and so on.
You go in fMRR preprocessing for run 4. Again, you turn off the slice scan time correction, and for the high pass filter, you set this to value 11. 11 cycles we remove. Then you go to options for the motion correction, and there now is a difference than before, because now we select here the file which was saved by the tool, and we now correct run 2 to run 1. Although it's run 4 to run 3, logically it's run 2 to run 1. So, and therefore we look here in these prepared output files, which is this one, and it tells you that's really your run 4. You see here, it's your run 4, but logically run 4 is run 2, and we align it to run 1, which is run 3, right? Because the tool uses logical names so that you can not have to be forced to use always run 1 as your reference. And what is now changing? It says, okay, I want to add this transformation, which is the transformation to go from run 4 to run 3, logically run 2 to run 1, which is added to each volume when you do the motion correction. Not as two transformations, it combines the local motion correction within run and adds for each volume this transformation. Then you have a transformation which brings each volume of this run 4 to the reference volume of run 3. Is that clear? And since I used the reference volume 4, I used the reference volume 4, I also use now reference volume 4. Now I say go. And now it will, and you see there's this is now important. It does not start at 0. You see the left side, it starts, these are the parameters, the motion parameters across the runs. It's small. For run, if you would go to run 1 or 2, it would be much bigger, because run 4 to run 3 is not so much displacement. So the plots have the added volume added, right? But you see the within run, volume by volume motion, the so-called frame-wise displacement, is below 0.5, which means there is no motion. This is the criterion people use. So if the FD is below 0.5, it's considered you don't have to remove these volumes or so. You can keep them, right? This is a nice threshold here you can use. Some people use a different threshold, but most use 0.5. And now you see that within run 4, there is also not much motion. A little bit rotates to the right, left.
I was wondering, so just to check if I got that theoretically right, so there will be more interpolation in run 1 and 2, and less so in the other runs?
Yes.
And why? But if you would use, let's say, the mean over all runs.
This we do in a moment, yeah. But we use only run 3, 4, 5, 6. You can use all 6, it's not a problem. But the more the transformation is, the more, for example, we do the undistortion correction, and the runs which are rotated away, the APPA will not work perfectly. So you get still some artifacts, because Renzo said yesterday it was recorded run 4, 5, 6-ish. So if we align these 4 runs, the AP to PA distortion correction will be working very well, right? And you can then average these 4 runs because the paradigm is the same, the protocol is the same in the 4 runs. That's one of the files I gave you prepared. Yeah?
Then again, the naming convention part.
Yes.
Why are you voting? Because I thought that, so I'm gonna have a look at, I want to show you what I know and then understand what I was trying to do. What is it still on?
Is das der High-Pass filter? No.
Oh, you have loaded.
You have loaded one of the first ones. I see this is a big displacement.
I understand, so.
You should start with run 3. No. So the second one is run 4, correct? Yes. Yes.
And then here. And
You
then.
just browse this one, yes?
This naming convention.
You have to go run 2 to run 1. And you must be careful. There should be run 4. Yeah, this one.
But this is the one I picked now.
Run 4.
Because I think you picked.
Yeah, it's perfect. Should be fine.
Okay.
Which brought it about?
And I think I did
If there's
everything.
if there's a Windows.
But I'm not sure why I saw so huge displacements. You shouldn't have.
If you can get the operating
It's
system.
strange.
CF.
Maybe.
Maybe you didn't run the right reference.
Yeah, then might not. I should actually.
The bottom line looks identical.
Yeah, it must be. So within run. So that's the nice thing now, because it has also the advantage, because if you go across runs in one step, but from volume to volume, then the within run looks different a bit, because it does not go. Here the nice thing is we always do within run, which has less iterations, because you have only to find to the reference volume, this volume to the reference volume, this volume to the reference, not to some far away run. So it's computationally more efficient, faster, and more precise, because we add the same transformation to all of these ones. So therefore, this looks the same, whether you do to another run or not. So, and you see here that the little motion in this run is corrected. It's a very nice run. You see also here, there's not much motion, a little bit. And we can do in the same way, run 3 and run 4. Run 5 and run 6. Yes. So at the end, you should have done this for, I give you a bit of time.
So can you go through that
I
one
will.
more time?
Can
Can you go through that one more time for the run 5?
Yes, okay.
Yeah.
I will do this. I just want to mention one point. We will not do the undistortion correction, the API correction, because it takes some time. We just go now next to averaging these 4 runs without distortion correction. But then we use the downloaded file where I have done exactly the same, like I do now. except I also run the API distortion correction. Right? So what we do now, we go to run 5.
Now they're five, so we on 5, 6.
5 and 6, then you are done. Go to run 5. And I'll go to pre-processing. And this, I think you wanted to see. We turn off the slice scan time correction like for the other runs. And then here, we go to options and we browse now, because that's our logical run 3, run 5. We go to where is run 3 to run 1? Run 3 to run 1 is here. And it says it's your real run 5. It's correct. If you can confirm. It says logically it's run 3 to run 1, but it's your real run 5 to run 3. Okay? And I say, okay, just for consistency, get this here to 4. Actually, in Brain Watcher, some people like this a lot. These things you do are put in the file name. So the file name grows, but it tells you what you have done. It will tell you which reference volume you have used and things like that. And it has this funny new ART, which says, I have a cross-run motion correction with a transformation file. It's not giving you all information, but it gives you at least some information. Is it okay now?
Yeah.
Good. Then we put this here, the high-pass filter to 11 cycles per run. Our protocol has 12 repetitions, so we should not go 12. We remove our effect, but we can go to 11. And then I say go. We have now the 5th run motion correct. And then we do the 6th and we are done.
Who is the yellow skin person?
This is my wife, Claudia. Without hairs because MR. And this is already 30 years old, almost 25 for sure. More. It was in Frankfurt I did this already. I like to see my wife from time to time. And then we now use the BBR. We want to now do the co-registration of our functional data to the MP2 range to bring it then in our 0.3 space. You see the run 5 has quite a bit of motion, up and down a bit. See now? But it's corrected quite nicely. So that was run 5. One more to go. Again, this can be scripted, except that the new commands use this transformation file has to be added in the Python. I will do this before release. So you can script all that, right? Oops. Now I open run 6, the last one, unprocessed one. 4, 5, 6, this one. Then we go to fMRI data preprocessing. Select the run. This is our logical run 4, which we go to 4 to 1, which is this guy that tells me again, it's my real run 6, logically run 4 to run 1, the last one, right? So I select this file. I mean, if you want to know what's in this file, just open it as a text file. You see, it's a very simple file. It just has the X, Y, Z rotation, rigid body parameters. It's all this is in this file, going from one run to the target run, right? That's all. And this matrix is just added in each volume, the same matrix for the within run motion correction, plus this transformation file for each volume.
This between run, you are computing between single volumes of the reference run and the target run, or do you? So when you say run 3 to run 2, let's say, Is it taking just the first volume of run 3 and the first volume
Yeah.
of run 2?
Yeah. But you can also, for example, wouldn't do this, they're not yet motion corrected. You could average them or use another one, any reference. But since you still have motion, I don't average them. That's what I want to first do the motion correction.
Also do like within that thing, just take 5 volumes, do motion
Yeah.
correction of the 5, and then
Yeah, you could, yeah. Yes. But I tried to play it with this, it doesn't change, because, at the beginning, the first volumes,
and depend on how much content.
yeah, that's true. That's true. So then I select our last one, logical run 4 to run 1, 6 to 3. And just to be consistent, keep this here. Say okay. Our high pass filter is 11. Say go. This is the last one. And now the nice thing is that all volumes of all 4 runs are all aligned to the same reference volume. So they're all now aligned, right? Like one long time course over 4 runs. And since we have not much time anymore, only half an hour or so, I want to now not do the API distortion correction, which you could do, but I have gave you a file and averaged already these 4 files. So I have the same done what you see now. Then I add for each of the motion corrected files, I added API distortion correction, APPA, and then I averaged run 3 to run 6. I can show you how to average run 3 to run 6, but without the API distortion correction. But we continue then with API distortion correction. Yeah.
So I guess in the Brain Warrior documentation, is there a flowchart somewhere that has all of these steps sort of mapped out? Yeah.
You find a lot of information about all these things, except this very new stuff is not yet in the documentation because you have a beta version here. But when it's released, there will be an updated user's guide where all these things are explained. So now we are done. So how do we average all these 4 runs? And assume for the moment we have already done API distortion correction. Actually, just if you really want to run it, you can. You just go to the plugins, and there is this copy thing. Just open that, and then you can do the API distortion correction like I showed yesterday. Yeah, we just skip it. How do you average the 4 files? Let's do that. So I have lots of files open now. I close the unpreprocessed one. BrainWatcher opens automatically the preprocessed ones. And these are the ones you want to average. So I go in options, and there is a menu which says average FMR STCs. So average my functional data. You see that in the options menu. You go down and you find average FMR. FMR stands for functional data. So, and then you can, it has usually already one. And now you use the file names, which have preprocessed file names, right? And you just add, one is already there. The last one you have probably used. In my case, it's run 6. You see, it's already there. So I only add now run 1 to run 3 to run 5, because we average 4. So I look now where I have my preprocessed run 3. This is this guy. I add it. Then I add my run 4 preprocessed is this one. And then 5. And then I'm done. 5 is here. So now I have all the 4 files we want to have after preprocessing, after motion correction, after high-pass filtering. No smoothing. We could, of course, also smooth, but we don't do this. And now I say here just go to average them. And then we have, in a moment, a file which has a name like average files or so. We can rename this to make it a bit nicer. So now mine is done. This one is not automatically loaded. So you go in open and you see average N4, 4 runs average. Of course, this is not a nice name, and this, normally I don't like to do this, so I should have given it a nicer name. But you can also use the name of our runs, copy it, and just add average in front, and then have the similar name as before, or at the end, however you want to do it. And there is now a file. So I just don't rename it now. Here, just to go here. And then if you run the statistics, general linear model single study, on this one, which is now the average of 4 times 12 trials, you will get, your computer explodes because you get so strong statistics, right? This is just insane, right? Look, this frontal activity, Federico, the frontal eye field. Look, and with the 4 runs, you have more errors coming up. It's extremely strong. Bit of attention in the frontal eye field. You attend to your checkerboard. This could be, I don't know.
And that's water, maybe? Is there a task?
I think there's no task. And so there was no task, right? It's just passive viewing, or did they have to press buttons? No. Yeah. That's what I thought. But I mean, this is undisputably mega strong, but even these other errors, which you not see so often, are coming out nicely in passive viewing. So now we will use this average file for the co-registration. And actually, to make it even better, we now average all these volumes into one, because they are nicely motion corrected. So we have already 4 averaged, and now we average all those. And then we have a wonderful file for BBR for finding the boundaries. So let's do that. Last thing before we do co-registration, we go in options again, but this time we go in the function saying average VTC over time. No, not this one. Sorry, it's wrong. Average FMR, it works also for VTCs. Average FMR over time and convert to IMS. This button, you use this one. And don't change anything. Just say OK. It will not use any bilinear interpolation because it keeps, we don't change the resolution. You can turn this off. Keep it also on, it will not use it. And you just say OK. And then you say something like grand average or so, right? This is really your average of all motion corrected volumes of 4 runs.
I think it's the AMR file and then open the top one.
No, but it also writes usually under its own name an FMR because we want to use the FMR.
I know.
Yeah. But for some reason it does not, I forgot to, normally when you produce a file, I add it to the licensed files automatically. Maybe not in this function, forgot maybe. Because I cannot open it myself.
That's not.
I can.
You can? Good. Maybe it's something wrong. It's good if you can open it. So if you have this file average N4, volts averaged, this is the one we need, but I cannot open it. Of course, I have brain motion next, so I can just open it. But I want to play nice and only do what you do. So doesn't matter. The files is also prepared in the prepared downloaded files. So, but now we do something important, namely we want to use now BBR for co-registration, but we first want to help BBR and give a close starting point without manually doing anything. We just use the header information between the two volumes because it's in the same session. So they're already pretty close, you will see in a moment. So what we do is we open our anatomy now. So we go back to our anatomy folder. And in this folder, we have a file, our file. Sorry, just press the button. So open in your anatomy folder. This brain file, right? So we all produced, I think, this brain file. If not, there's also one in the prepared files. We just use this, not the 0.3, you used the one before, right? We called it reframed brain. This one we open. To this, we want to now, that's why we need this file, because it has not a white matter, gray matter already. Then the alignment is difficult because you need intensities. So this is the original file where the skull and everything is removed by the DNN network, right? So, and then we go to the 3D volume tools again. I have always this, make it large. The zoom thing is in front of me. So, and then you go now to co-registration. And in Brain Voyager, co-registration has two steps. Initial alignment, which is just using the header, and then some fine-tuning, several methods. We will use BBR. Fine-tuning means make it really, really nice. So we do the core step. We say select FMR, and now we select this averaged volume file. If it doesn't work for you, you can also use one of the runs or the average runs. It doesn't matter that much, I found. BBR is so robust, but nonetheless, best is you use the averaged, one of the averaged ones. IA, just IA. You press just IA, not so fast because yeah, you're faster than me. That's not good because most people will be slower than us, probably. So Volt's average, probably use this one. Doesn't matter too much. You get something like this then out. So if you you should see something like this, where you see that it is not perfect, but the overlay here, you see, you can do this in different ways. You can also toggle back and forth. If you go here, you can basically, compare the two. Looks not completely wrong, but it's also not perfect. But it's good enough for BBR. And the nice thing is when you do this IA step, Brain Voyager automatically saves a file called for BBR. It's automatically there. So this is what we load next. So you go to open and you load the file. Should be somewhere in the functional. And there you find, hopefully, a file. I don't find it. This? This one here. Yes, I see it. Yeah.
But how did we get that file?
If you do the initial alignment, that's a nice thing. It does it fully automatic. So it brings the functional slab close from the header, close where it belongs in the MP2 range, and then it just saves it as a file for BBR. Right? And if you open that, you just see the slab aligned so far as we are. And of course, you would then think, oh, now I do one slab thing for ER, then I do another one for BBR, and you accumulate these resamples, even if you use Windows Sync or Lancos, which are very good ones, but all GPU accelerated, by the way. But the point is, we do this at the end, all in one step, just to get intermediate results. So now, how do we do the BBR? We basically have just to load a mesh. And we had which mesh to load? Our mesh which the DNN segmentation produced for us. We can also create one from the MP2 range quickly. Brainwater can also do this. But since we have so nice ones from the DNN segmentation, we just now go in load mesh, go in our anatomy. There's one little problem. We have them separated for hemispheres. Now I don't want this. I want them.
The top one is combined with it.
Yeah, I did that, but I want to show how they can do it, right? So the point is, you will not have this. This is one I prepared. Or did we do this already? You have this also? LH? This is the gray matter one. No, don't use this. We need the white matter one. This is the gray matter one. See, it's white matter, gray matter. So it's yeah. So therefore, what you do, you open the LH Rico Smooth, and then you go in meshes again and say add mesh, right matter smoothed, right hemisphere smoothed. You go in here, and then you merge first. Cannot save now. You go into scene, because it's a scene of two meshes, could be more. And then you say merge meshes in scene. You can actually merge many things, but we only do the meshes. And then I say here, just to have a bit more nice name, merged LHRH. You can also keep merged and rename it as you want. Then you say merge, and then basically it opens this. You have it here merged, you know. And this is the file we need. It's already linked to the BBR volume, the slab. And so then just that you see, when you right-click this menu, you say project in VMR. If you click this, you see already the mesh here in the VMR. So the yellow line is now the mesh projected in our volume. And it's not too bad, but it's not perfect. We have not yet run BBR, right?
It's different sessions, though.
It's different sessions.
Yeah.
Why is the header
Maybe lines consistently.
Interesting. You use auto-align, then it's like this.
Yeah.
We use auto-align to have exactly this, that over sessions you still have quite the same, you know. Actually, it's a good thing to use auto-align. For neurofeedback, it's amazing because you can have a patient next month. It's just the same, more or less the same slices, right? It's very nice. So that's all. We can now run a BBR, should be close enough. And then I go in meshes. I first need to highlight the meshes. And go here in meshes and say, let me see, boundary-based registration here in meshes. And then you just say go. Actually, if you align to T1, you can do, I did this for Vaso. Then I had to switch this to this one because it must know which is white matter brighter or gray matter, right? Since this is a kind of a functional one, a non-null bone from the Vaso sequence, we keep this and then say go. This is not as good as Vaso, the result from the numbers, right? But it still works pretty well. So you see now here in the left log here, the starting value before is just doing it now was 0.98, which is typical around 1 before you align. And now at the end, we have 0.3. That's okay for this data with not much contrast between gray and white. So that means it has worked. How do we know? So here, I closed it. You see this volume of interest file. The first one I did, just delete it because I don't want my own one. These are the two ones which BrainWatcher automatically creates. It says this was the alignment before we did BBR, and this is the alignment afterwards, right? And if you look, for example, here where the visual cortex is, you see very nicely how we capture that. It's not so well visible. That's why also the value is only 0.3 at the end. But it's pretty good. You see it maybe better here. You see here the contour, how it nicely follows the white matter, which is a bit darker, and outside is white, which is the gray matter. Also here, you see how that nicely follows this. So this worked very well, despite not much contrast differences between the two. So this is so good that you not necessarily need arms. I think it's not needed because you see the, Federico, see this? It follows here the boundary pretty nicely.
You know what he used the distortion corrector? I did.
Yeah.
So now we have all the pieces we need. We can now go to the layers. You have a bit of time. Let's do it. Because now we create a functional file which is big, which is like 10 gigabyte or 12 or whatever I saw. It's also downloaded, but I just do it. It takes only a minute or two. It's not very long. So if you have enough memory on your computer, try it. But now I show you something, how we get there. And it's the last thing, and we can do layers. Yeah, don't care. Oh, yes. Okay, so we load again, close everything for now. And then you open up again this brain file we used for co-registration. The same one, because this is our host. We now bring the functional data to this and go on to our 0.3 space. We had here done the BBR to this one, right? And now comes a function which is also fortunately scriptable. It's a bit a long one, but I show you this in the graphics. You say create, it says normalized or standardized, what does it say? Create normalized VTC from fMR data. Normalized can be any space, can be MNI space, can be ACPC space, can be native space, whatever you want. You can just bring it in the brain space, right? But we go a bit further. So when you click this, you have lots of options, and a few I have to tell you, which are important for our case. So the first is we select here our average 4 files fMR, not the one volume, then we only see one volume later on. We still want to have our 200 volume time course, but averaged over 4 runs. This is the one we select in the functional folder. And it is not this volts average, but it's this one, which is the runs average, right? It's important that you select the right one. And then we have the IA, so the first transformation from the header base, which worked, although it were 2 different sessions. That's nice. And this is called IA. You have this one here, brain IA, F. And then this one, FA, this is the BBR, this is the fine tuning. And it says, it has here, produce the BBR process, spits out some files. One is BBR_FA, fine tuning. This we select.
So those files are, you don't have them shared, do you?
I did.
You do.
Yeah.
Because my alignment failed. I used the sorted one.
Okay. Yeah. Yeah, then it fails. Yes.
The correct files.
Yeah.
Okay.
Also, the file comes out. Is also you can also download. It was there. But now comes the point. So this is important now. 2 important points. Can Renzo listen a moment? Just a moment. Because it says on the left side it goes to native. So if we now would say go, our data would be, which I usually did when I tried it first, go in our 0.75 brain MP2 range space. But since we want to go further to 0.3, we click the button to ACPC. And then it opens up a new entry. You know, if I say to ACPC, then it says, I can specify a so-called ACPC file. And that file is the one, the combined ISO 03 ACPC, which you also have downloaded. You can also create. Because this brings us to the final space, which is this file here, combined ACPC ICE 03. But we can still not say go. The reason is, it would by default now create 1 by 1 by 1 millimeter 0.3 files, which gives you 50, 80 gigabyte on your computer, right? Don't do this. So therefore we go in options. You can do this, of course, if you have the memory. Otherwise, don't do it. In options, and you see it's 1 by 1 by 1, because BrainWatcher, since recent versions, never wants to go to lower quality than you have. And it says, no, you can't have these big boxes. In the past, it stopped, said, huge data, please don't do this. It's gone. But I still like it sometimes, like for this data, and I want to have 2 by 2 by 2. Since we go not to 1 millimeter or so, we go to 0.3, the actual resolution will be 0.6, so we still oversample our data a bit, from 0.8 to 0.6. I would not go to 3 by 3 by 3, which gives you very nice small files, but then you have only 0.9, so you have no longer your original data qualities. I would not recommend that. So therefore, we go to 0.2. But we also need to say 512 because we know that and that is actually the original reason that this program knows in which cube the anatomy is, so that it brings it in the same cube, you know. And finally, the last thing we have to do, no, that was it. So we have 512 and 2 by 2 by 2, that's all. And we want sync interpolation to make it really high quality, right? And this runs here on the GPU. Then I say go, and you see here, it spits out everything. We use the undistorted average one. We have 512 box, we have sync 3, we have 2 times 0.8, but in 0.3 upsample space. Actually, this I will add here at the end. I will add some, after ACPC, I make a minus sign 0.3 that I know, this is in 0.3 space, VTC. Right? And if you now say go, this is quite a huge transformation, but it's all done in one resampling from the fMR to this space, one resampling. That you saw it's not very slow. So this sync interpolation on the GPU, it runs quite fast. Yeah. And then we look at that data because there we just draw and see our layers. I'm pushing a bit because I see the time is running. I think if you only have looked, it was a bit fast, I know. I write a tutorial at the moment. It's already most steps described, which I will send Renzo to, or maybe Luca. Luca, you send to the students, right? You can distribute that, and you can actually go yourself in any pace you want through exactly all these steps, actually more than those, also with undistortion correction and so on. And many things I have not the time to show you. So you will have this soon, maybe in a week, and then you can do this at home on your computer. And there's also, if you want to use BrainWatcher more, a getting started guide, which you should run through just to get familiar with all these concepts in BrainWatcher and how it names files and things like that. And then there's a user's guide, a very big thing, also as an ebook. You can actually read about these things.
I think maybe when this is completing, another thing that is nice is that when you create these files, if you, for example, don't care about the whole file, you could even reduce the box on which the file is being created. So for example, you can specify XYZ box sizes and say, I want the VTC only around this cube.
That's what I use for the ARNS integration.
Then when it does this, it's nice because the VTCs gets even smaller. So then everything after will run faster. So if you have collected the whole slab, but all you care about is V1, you could create a box around V1 and then, you know, your file would get much smaller.
So how big is that file? If we go now in our output folder, in the functional one should be, there will be now, it's still coming, 8.11 gigabytes, just copying it here over. I think my computer will be complaining. I have only 30 gigabytes, I should be careful. Okay, you see here on top, this file is, it would be an ARNS 50 gigabyte, right? Because it does not use any, 8 times 8, 64 an ARNS. if you use floating arms. So, and now the nice thing is, really nice thing is, if you now open the anatomy in 0.3 space, you can very fast now look at your data. And actually we had the brain in that space. And there's also a prepared white matter gray matter file for time reasons. Please open this file because we cannot clean it now. We have not the time anymore. So use this file, which is our ACPC ISO 0.3 file, with some cleaning like tissue homogenization and labeling white and gray matter voxels, right? So if you open this file, it should look like this. So it has only tissue for white matter and gray matter. And now, how can we do statistics in this space? We simply use link VTC and select our big file we just have created. So in functional processing, we select our big file, 8 gigabytes, just now created today at 10:51. So I select this one, say go, and then the nice thing is Brainwave doesn't load the whole file. It just reads it when whatever voxels you click, it reads these voxels in memory. It's very memory efficient. That's why it runs on your tablet. And if I do now the same function, general linear model, I can now run this in this very big file. Just say define predictors and say go. And now it takes a bit longer, but I get my results in the 300 micron space. This is, I did yesterday the VASO. I showed you the blue colored voxels because it was mainly, I didn't flip the data, which you can. But now we get bold, so we should get a lot of red colored things like before, but now it's in our 300 micron space. So it's already done. You see, this is now, look at the data, how big, how strong it is. And it looks, it is extremely precisely aligned, although we had a huge transformation, right? So now, if you want to toggle somehow the map, you can go and open this volume map again, like we had in the DNN segmentation, and you can just here toggle on off, and you see that the alignment is really pretty well done. The bold is a little bit, is this huge effects. I should make a stronger threshold to sharpen a bit. This is bold, it's not VASO. So I just make the threshold not 2.8, I make it like 5, just for now. And make the upper color to see a bit more range, like 12 or something. This is just for visualization. And turn it on again here. It looks already nicer. And you see now when we toggle this guy, for example here, it looks pretty nice. See also here. Looks slightly better on VASO, but it looks pretty nice. So now I have sent you also, just to save a bit of time, I prepared you because we have only 5 minutes, I prepared 2 regions of interest, right, which we can load. And then we can directly see do the laminar stuff. So you know what regions of interest are? And what I do now, show this a bit. You open the volumes of interest dialog, and then you load the prepared file, which are exactly the 2 ones I showed for VASO yesterday. So you open the file, which is called visualareas.voy, this file. So this file you should have in your downloads. And if you load this, you see them, actually see them here, green and red. Of course, red in VASO was nice, the color, because you saw it. But here we don't see it very well. So I will change red to blue here, just for our purpose, so that we have the color visible. Now you see my draw, here I draw this region, and I draw this region. Directly in this dialog, you can draw. And now I say I want from the green one, I want my layerification. Okay, very easy. And now I not use any surface. Today, no surface. So what I do, we just go back to, where's my boy? Here, and the other one's here. I use this one. And then I go in the volumes, not surface, and say I want to have a grid, but I don't do a grid. I do grid sampling, but what I say I need is, I have a thickness file. You should have, there's one step missing, I forgot. You need to calculate a thickness file. Let's do this quickly. We will manage.
We have time, take over.
Yeah, okay. Yeah, okay, thanks. So then what I do, over this file, we now calculate a so-called, I don't need this. Particle thickness file. So I just want to turn this guy off that we not get confused. So now I go in the volume and say, calculate for me the Laplace equation and do a cortical thickness thing. We use this as input. It has already gray and white matter labeled. And then we say, just go. And what it does now is it solves the Laplace equation for the 300 micron very fast. And then it does also the distance metric, right? So how far is from white matter each voxel away till CSF? It does this now. And then we can just use this file and see do the layerification. And then we are good to go. Just a moment. Now it visualizes the result. This is now, if I go in volume maps, you can select, like in the DNN segmentation, you can basically select here, for example, this is the cortical thickness. We have also white matter distance, looks already like layers. And we have also the Laplace smooth thing, right? So we have all the things now here. Also the gradient, which it calculates to do actually these other distance. This is the one we need, the white matter distance. But it does it automatic. We just give it a thickness file and it does the rest for us. So what I do now, I go into the last thing I want to show you. We go in volumes, we go in high-res cortex depth grid sampling. And then there we have now the thickness automatically loaded. The only thing we have to do now is to determine the number of bins. Here it's set as 10 as default. I keep it like that. You just click depth spinning, right? And then it's already done. We have here our 10 bins. And actually, you can show them in isolation, the layers, but I can also just turn them all on. Go like this. You don't see much. Let me just move this up. You see them here. And actually, you can make them a bit more bright. You can make these layers or these voids here transparent. Like you see now, you see the gray matter. And now I turn on, and now you see the layers, right? Actually, it's still too... Just do a new one, smaller one, like that. You see now, you see it better, right? These are the layers without any surface. Just this is almost like Laney, what this does, right? And then you have your layers, and now we just sample the functional data from these layers, right? And that is very easy. We can just say, actually, for the moment, I remove these two guys because they would otherwise also be sampled. Actually, it's not bad. You get the mean of these areas, how much effect is in the whole areas, but I just remove it now and just say, show me a table with pooled for each of these voids. What is the effect? First, one thing I forgot. Actually, this is interesting too. You can sample the thickness map or the distance map, but not as exciting. So what I do, I load our statistical file, a statistical map file. This is still actually, for the fun, I just do it now. I turn on here the white matter distance as if this would be our checkerboard. And then I also still have our voice, yeah, our bins. And now what I do is I go here in options and say, give me a table with the effects. And now you see these are the other maps I didn't turn on, but this is the distance one. And look at this, you see, of course, that it starts from a low value and goes from the white map. So the first one I skip usually, but I could also add. So it's a little jump here, but then you see how nicely it goes up and up and up because the distance from the white matter to the gray matter, to the CSF, is in the distance map, right? And you just see this. This gives you this. But now let's look whether we get the same when we use, or something similar, not so nice probably, when we use the statistical map. So I load our checkerboard map. So I say load. Should also be somewhere. If not, I calculate it quickly. I think I did not save it. So I just will rerun this. This is very fast. And then you can save this also. Then you don't have to do this again. So I run this. And then this map here will be replaced by the p-values of our, or z-scores you can also use, percent signal change, of our checkerboard thing. So it runs now for all voxels, not just for those, then it would be much faster, but for all voxels which are in the gray matter voxels, see in blue. And it has now calculated, look how big these effects are. So, but now I will save it, so I have not to do this again. I give this here harder threshold. Even 5 is too low to just see a bit of structure. And then for coloring, I give it here a higher value. You see a bit more the T statistics. And then what I do next, I go in my 10 bins, go in options, show me that table. And this is now the table which actually shows somewhat an increase to the upper layers, right? But this is not the real data, right? The functional data. So if I press here plot, this is our result for bold. Yesterday for Vaso it was like this, a middle peak. Now we have a peak, not much of a middle peak here, or actually here should be an increase here in the middle. I don't see that honestly, but you see in this box, you can use others, you can try other areas. This is just one randomly selected one, right? But you see at least you get the typical draining vein effect or whatever that is, right? And if you would compare this and load the other one, which was like this, you would see the difference of bold and Vaso. I plot Vaso exactly in the same way in that space, and then you can compare it. And you can add the T-map for Vaso and bold and get a plot of, you would see then 2 graphs.
I can add because at the moment this is sampling the value of the map. So in this case would be the T-stat.
Yes, correct. Correct.
So in the layer map or layer output, you showed the kind of in the underlay before, the like bin number 1, for example, was pretty sparse, right?
Yeah.
So this is a viewing thing, right? Or is it really the case that there are just 3 voxels that contribute to the most left point here?
It's also my drawing, you know, and then and normally I try to, it's a bit different than Laney in that point. Should change that because normally in my case I do not want the voxels outside gray matter, you know, and I should allow these voxels. So it deletes those because it's not gray matter. But of course you want to see maybe a little bit how CSF and how white matter, that you see a bit more the fringe, right? I was at the time I programmed that quite restrictive and said you should only show me gray matter voxels, right? But and sometimes it overcorrects there, so it's a little bit too sharply. So what I want to say is, the first voxels at the fringe of white gray matter, they might be not used.
Right. But if I would run in an 0.3 space with 80 gigabytes, or if I would not pick 10 layers but 7, I would have more.
Yes. I have actually a version of this one for 3. Can also load this. So actually, if it's on your, here, you have 3 bins. No.
Right. So each.
Look here.
Yes.
Here you have 3. And then I can do the same thing. I'm not sure what comes out now. Let's just see. I have not tried. You get the 3 values. Oh,
Yeah, big in the middle.
big in the middle. That's really strange.
So these are like unique voxels, right? Right. The assignment of the layers.
Yes, unique voxel.
One
Yes.
voxel assigned to one layer.
The binning is exclusive. Yeah. If you use the grids and create
Then you
bins,
can
not
have-
exclusive. Yeah.
But I think, for example, what you can do is you have the distance of each voxel in the distance map.
Yeah.
And you can export the distance and the t-stat and then plot it as a histogram over the distance space and not over the voxel bin space. So, but you need to write a code for yourself because the distance map is already there, the t-stat is already there. So you only need to put them together if you want to share.
So that was all I want to do. I'm a little bit over and not so much. And actually, this is the plot now I got from these voxels. And there is also a little bit of a, I'm not sure why I have now these ones. It's a bit strange.
It's a different UI compared to the
Yeah, it's a different one. So you find, of course, some variability. It's not each region exactly the same, right? So I just want to try one other ROI just to check this. Use this guy here, which is around this Celsius here. That is here connected, doesn't matter. We'll still remove this part here. It's just part drawing efficiency, you know. Go in the high res without the surfaces, but I need now back the thickness map. That was, yeah. And then I just bin again. Now I see the bins around the other void. And now I should be careful and load first, otherwise I sample the thickness map. I load the, did I save it? Still not. Oh, I'm stupid. I should have saved it. I have to run the statistics once more. Yeah. Doesn't matter. Fast. And then we sample from this, the layers here along this one. Of course, it would be nice to have two banks separated though, right? There's also a problem, actually, Renzo, which is very important. It's also here, I'm very much removing, that's what I mean. You could also make this, because in my tool to be safe that cells I don't touch, sometimes it removes a bit too much there. I will also change this so that you can have this a bit, yeah, but you see the bolt follows this beautifully around, see? So if you turn off this or turn off the bins, see, this is really nicely filling in. And that means our alignment is pretty good. That's really good. So now let's have a look. The first two I should remove. Otherwise you get a bit confused. So let me go here and make a plot in these guys. Oh yeah. So both is over 2 hours randomly selected, did not select by, is in the calculate. This is a little, two slices on top of the calculate. So maybe there you get even stronger effects, and maybe a middle peak, but here not. That was it. So if you have questions, you can also email me. And as I said, I will send around this tutorial, so which you can then go in your own pace through this. And yeah, and let me know if you have any questions.